Okay, so I apologize for not bringing my sheet, but that's basically the problem. And we want to write the variation of shear force and bending moment as a function of x. Typically, we're going to assume that x is always on the left and goes to the right. That's typical of Cartesian coordinate system. It is sometimes possible to change that origin and direction and make it simple for yourself, but I'm going to always try to maintain that from the left to the right. So if I did do that at x, what you could see is if I made a cut there, you have to ask yourself, do you want to work the left side or the right side? So if I look at the left side, it's triangular in shape. That's nice. But what happens over here? I need some reactions. If I go to the right side, well, I've got a trapezoid. I know that's going to be trouble. And plus, it gets a little trickier over here when you're working with these x dimensions. So I think it'll be easier and probably a little more educational now to do the left side. This will be a little bit simpler to get started. And with that said, then I need to find my reactions. So I'm going to come over here and draw a free body diagram of the structure. The first thing I'm going to do is get a concentrated equivalent of all this load. So it's a triangle. So the area of a triangle is 1/2 the base, 20, times the height, 2. That ends up being 20. And it's going to be 2/3 the distance from the small end, and 2/3 of 20. I know I can do that fraction, but I'm just going to call it 40/3. Two-thirds of 20. Now, on the right-hand side, my reactions, I'm going to write those in shear force and bending moment sign convention, because what am I writing an equation of? Shear force and bending moment. So on the left side, positive shear force is up, and positive bending moment looks like that. So that plus means that those are the positive sign conventions for those two things. Actually, I probably should label that. Let's just call that point A, and I'll put an A subscript on these. So that's the first thing I have to do is find those reactions. So what am I going to do? I'm going to come and I'm going to sum moments. Where am I going to sum moments about? Probably point A. That means I won't have to worry about the shear force. And when I sum moments about A, what do I have? I have my moment at A, and with right-hand rule sign convention, this moment is negative. The 20 kip equivalent force about A is also creating negative moment, and it has a moment arm of 40/3 feet. Sorry, I kind of jammed it in there. So the moment at A looks like it's going to be negative. I don't know, what is that going to be equal to? 266.7? Is that right? Yes.
Why aren't we finding AY first?
I am going to find AY. AY is shear force. But we're not going to call it a reaction. We're going to call it a shear force. So what was the answer? I'm sorry, was it 266? 266.7. Can't have 3 6s in a row. It's against my superstition. And then I will sum forces in the y direction. I will assume up is positive. So this shear force is up, so that's positive. This load is down, that's negative. So it looks like my shear at A is 20. So my equation better predict at x equals 0 that I have a shear force of 20 and a bending moment of negative 266.7. I know where I'm starting. If my equations work, I should get that. Oh, by the way, what should the shear force be in my equations if I check it at 20?
Shear force?
Yeah. 0. What's the bending moment at 20 feet? 0. So I know conditions that my equations need to meet. So once we derive these equations, if they don't meet those conditions, then you got a little guidance that you've done something incorrectly. So now let's write. I'm going to draw this a little bit bigger. I'm going to draw the free body diagram of my structure cut at some distance x. And I'll let you know which direction we're going. I already know at my far left side that I have a positive shear force of 20 kips and a negative bending moment of 266.7 kip feet. Yeah?
Shouldn't shear and moment at 20 feet actually be undefined?
No.
Why is it 0?
Well, there's nothing there. There's no beam there. Well, I'm not guessing. Look just to the right of that. You're in space.
Right,
Space doesn't do good at bending and shear. Now, if there's an applied moment at the end, then I know what the bending moment is there. But there's no applied moment.
But if you do your equations, won't it come out as undefined because it's a discontinuous point? Okay.
Just the reaction of A from total will come back down.
All right, we'll see it.
Okay, so let's figure out what our equation is here. So I know I have this load. What's the intensity of that right there?
2 over x.
Basically, what I need to know is what's the slope of the line. Rise 2 over run 20. 2 over 20 is 1/10. So this should be x over 10 kips per foot. Does it work? Well, when x is 0, what should I get? This says I should get 0. When x is 0, I get 0.
Yes.
When x is 20, what should I get? 2. I put an x in 20 and I get 2. So anytime you can match a linear line with 2 points, you're done. It's unique. So, what is the concentrated equivalent force of that triangular load?
X squared over 10.
Well, remember the force is the area of the curve, and what's the area of the curve? 1/2 base is x, height, x over 10. So what do you get? X squared over 20. And that will have units of, I know it looks odd, but it has units of kips. So I'll call that's the force. What's the distance, d, from the big end? It's normally 1/3 the distance. And what's the distance? X. What's 1/3 of x? X over 3. Now I'll go to the side I'm cutting and I'll assume positive shear, positive bending moment. Oh, holy cow, it's way past time. Either you guys are very, very kind or you're very, very interested. I don't know which it is. I will continue, and for those of you who need to go, I'll just put the video online. You can watch it. It won't take that much longer to do. All we have to do is what? Some moments about the cut. So look at my free body diagram. The moment is positive. The force about the moment, about the cut, is positive. And the force is x squared over 20. And the moment arm is x over 3. Then you go all the way down here to the end. You've got my shear force creating negative moment. It's 20. And what's the distance? X. And then don't forget all the way out here on the end, the 266.7. With this sign convention, it is positive. So solve for the moment. It's going to be a function of x. And what's it going to be? Well, I like to put a bracket here so all the terms will have the same unit. So to solve for the moment, all those go to the other side of the equation, and you'll have minus x cubed over 60 plus 20x minus 266.7, and that result will have units of kip feet. What do I know about the moment? I know the moment at x equal 0 is what? Negative 266.7 kip feet. Plug in x equals 0 here, and what do you get? Negative 266. Correct. What is the moment at x equal 20? The magic point that Mr. Van Tilburg likes. I don't know. Plug in x equal 20 here. What do you get? I think you're going to get 0. I'll go ahead and check it off because I know it's true. Wait, we're not. You want to see the very end, or can you hold on? Okay, good. Some force is in the y direction. If you need to walk, walk. So what do I have? I have my shear force is down, so that's minus shear. My force is down, so that's minus x squared over 20. And my 20 kip is up. Solve for the shear force. What do you get? You get minus x squared over 20 plus 20. And that should all have the units of kips. What is the shear at x equals 0? Positive or negative? Does my equation predict that? Yes. What is the shear in Tilburg space?
0.
Is it?
Yes.
Put in x equal 20. What do you get?
0.
It works. Now here's the magic. Is there a relationship between moment and shear?
Yes.
That's right. The derivative of the moment with respect to x is the shear. Is that true, or is that just anecdotal? Right now it's just anecdotal, but we'll find out it is true. Very soon we'll find that out. All right. Thank you for your patience.